what's a forecast monitoring or a control? So if we use a particular forecast model, then we should be sure that the values given by such a forecast models are within statistical bounds or within statistical control. Uh, so this particular methodology which we are discussing, it's about monitoring and controlling forecast, and that methodology goes with by the name of tracking signal. Now, what is a tracking signal? What is that methodology about? With tracking signal, we establish that a particular forecast model exhibits what we call error bias or not. So what was the error bias, if you think about that? A consistent one type of error, either positive or negative. And we discussed what's a positive error. So positive error is what we call a consistent. If we consistently underestimate a particular actual value, or what's a negative error is when we consistently overestimate the actual value. So consistent underestimation and a consistent overestimation gives you error bias, and tracking signal is a methodology that numerically detects that problem. So how this tracking signal works? So tracking signal works in some way like this. So you got a central axis, and in between you got a central line, which is a mean value. And we place a particular bounds above and below. And let's call these bounds as a upper bound. So I'll just call it an upper bound. And this value right here is a lower bound. And we fluctuate a particular error given by a particular forecast model in these two bounds. So if the error is fluctuating between these two bounds, upper and lower, we call such forecast model within a forecast control or within a statistical control. Above that central line, the errors are positive, and beneath that central or mean line, the errors are negative. And this axis is scaled with a unit that is called mean absolute deviation. What's a mean absolute deviation? It's also a methodology that summarizes a forecast error, just like MAP. So that stands for mean absolute error. I mean absolute, sorry, deviation. So what's a mean absolute deviation? It's a methodology just like MAP, but in MAP we consider mean absolute percent error. Here we don't consider percentage. We only consider its deviation, right? So that's the unit. So how much is that unit? We'll get into that discussion later on, but let's talk about a model, a forecast model that is maybe not in a statistical control. So a consistent one type of error. So for example, consistently, and we discussed that in your previous lecture as well, a case which we observed when we apply exponential smoothing on a particular data. So you get a consistent positive error. So if the forecast model consistently make a positive error, so this line will fluctuate only on the positive and it will touch the upper bound, and at some time in future it will cross the upper bound limit. And that is when we say the forecast model is not in control. So if the fluctuation is within these two bounds, we call the model being a forecast control. Or it's in a statistical control. But if it crosses that particular upper bound, or maybe if a forecast model is consistently giving maybe a negative error, or we are doing overestimation time and again, it will touch the lower bound and it will cross it. Such kind of case, this one and that one case exhibits the feature of what we call the error bias. That is the whole concept of tracking signal. But now the question is, how much should we take these upper and lower bounds? And I said that this axis right here is arranged in units of mean absolute deviation. How is that? So there is a statistical bound for it. So it is already estimated that plus minus 2 MAD is equal to about plus minus 1.6 standard deviations. Plus minus 3 MAD, or mean absolute deviation, is approximately equal to plus minus 2.4 standard deviation. And plus minus 4 MAD is approximately equal to about plus minus 3.2 standard deviation. So why are we discussing those? You might have came across a rule in your statistics course that almost all the observations should lie within 3 standard deviation, plus minus 3 standard deviation. If any observation that lies above or below plus minus 3 standard deviation, we call such observation as outliers. So the same concept is applied right here. So how is that? It is estimated that in plus minus 2 MAD, approximately 89% of error should lie. In plus minus 3 mean absolute deviation, about 98% error should lie. And in plus minus 4 mean absolute deviation, about 99.9% error should lie. So now here you go. That's the limit. So if I say it's a plus 2 and a minus 2, so in that particular bound, about 89% of error should lie. If I take a 3 and a minus 3 bound, so this means in that particular bound, about 98% error should lie. And if I take a plus 4 and minus 4 bound, then about 99.9% error should lie. So that is how we select the upper and the lower. So which MAD to go for? Should we go for a plus minus 2 MAD or a plus minus 3 MAD or a plus minus 4 MAD? There is no consensus amongst the decision maker on the value of MAD selection in tracking signal. However, a standard rule for selecting the value of MAD is something like this. The limits which we choose should not be so small that it can trigger it can be triggered with every small error. So if we take that limit so much small, then maybe a normal fluctuation or a normal error could basically tell us that this particular forecast model is not in control. And it's not the case. Why? Because we took that limit too small. And secondly, the limit should not be taken too much large so that it can hide a very bad forecast. So it depends upon how a decision maker takes a particular forecasting scenario. So if they are more conservative, more careful, they might go for a more lower value of bound. So maybe they might choose a plus minus 3 MAD or a plus minus 2 MAD. But if they have a certain kind of a flexibility, they can go for a plus minus 4 MAD. So it depends upon which standard you take, and then we decide that either a forecast model is within a statistical control or not. Now, mathematically, what's tracking signal equal to? The tracking signal is equal to, so I'll represent it with the TS. Tracking signal is equal to what we call a cumulative error. So what's a cumulative value? You should know that. If you don't, I'll make you understand in the examples that is about to come. Divided by the mean absolute deviation value. So what's MAD equal to? So mean absolute deviation is simply equal to whatever is error. So actual value minus forecast value, and we take its absolute value, we sum them up, and we divide it by n. So this particular value is taken in denominator, and the cumulative error is divided by MAD, and we basically get the tracking signal value, and then we compare it across the standard which we selected. So let's discuss one case, and let's categorically estimate the value of a tracking signal, and then let's decide that is a particular forecast model is within the statistical control, or is that particular forecast model in control or not. So for that purpose, I'm taking this particular data, and before proceeding, let's plot this data. And if we plot this particular data, it should tell us about the data component. So it has a strong trend, so a strong positive trend. So what if we are using exponential smoothing? So the exponential smoothing, the alpha value should be somewhat high, that is close to a 75%. So for example, we are using exponential smoothing with a 70% alpha maybe. So let's suppose a 0.7. We take right here, and let's estimate the value using exponential smoothing. So the first value is through naive forecast, and then we apply the equation of exponential smoothing, which is a previous forecast value plus the alpha value, and we fix that right here, and then we multiply it with the subtraction of previous actual value minus previous forecast value. That is your exponential smoothing forecast value, and let's drag it down. So the objective right here is not to forecast it for the next period, that is a period 16, but to check either the forecast model is within a statistical control or not. So starting with the steps of how to estimate the tracking signal value. So the first step is to estimate error, and you all know at this stage how to estimate error. So estimating error is simply subtracting forecasted value from the actual value, right? So that is the error in the first observation, and just drag it down. So here we go, we got all error values. The next step is to estimate the cumulative error. Now, how to estimate the cumulative error and where we use the cumulative error value? The cumulative error value is used in the numerator of the tracking signal value. Now, so the first cumulative value is equal to this. And since it's a cumulative error, so we are supposed to use column E or error values for that. So the first cumulative value is this. The second cumulative value, we take it, the addition in a diagonal. So this value plus that value right here. And similarly equal to this value plus that value right here, and double click. And if you check it out, so each and every preceding value is the addition of the values added in a diagonal. And one thing more you should notice, that the last value of the cumulative error should be equal to the sum of all errors. So if we add them all together and if we get the value, so this value is exactly equal to that value right here. So that's the cumulative error. Once we estimate the cumulative error, then we estimate what we call an absolute forecast error. So I'd simply call it absolute error. So that's the error. Let's estimate its absolute error value. So once again, I'd use a function ABS. And let's take the error value right here. And here you go. That's the absolute value. So it simply converts the negative value into positive. That is the function of absolute. Now, the next one is to take a cumulative absolute error. What does that mean? So that is an absolute error, and we are supposed to take its cumulative value right here. So how are we supposed to go about this one? So the first cumulative value is this. The second cumulative value should be the addition of this value with that, and so on and so forth. So if we drag it down, here you go. This last value is basically the sum of all these values. And if we check the calculations, so each and every cell, the value of cumulative absolute error is the addition of the values in a diagonal. Now, once we estimate this one, the next step is to estimate the value of MAD or mean absolute deviation. And you get the equation that is a cumulative error divided by N. So what to do about this one? We are supposed to take the cumulative absolute error value, and we are supposed to divide it by the value of time period, or in this case, N value, right? So this is the first MAD value. And if we keep on going in the same pattern, so this value divided by that time period, and this value divided by that time period, and so on and so forth, right? Now, finally, we need to estimate the value of a tracking signal, or TS value, right? How to estimate that? The equation simply presents that we need to divide the cumulative error by the MAD value. So what's that? So it's equal to, where is the cumulative error? That's the cumulative error. This divided by the value of MAD, which is right here. And that is your first tracking signal value, which is a plus minus 2. And if we extend that, so you see some values are negative, some values are positive. Let's plot that. And let's suppose we took a standard right here of plus and of plus minus 4 MAD. Plus minus 4 MAD is our standard right here. So if we take a plus minus 4 or standard, so this means that the upper bound right here for this forecast model, we took plus 4 value here and minus 4 value right there. Let's plot it and let's have a look. So if we plot these values, and you'll immediately notice something. So you see, somewhere around which observation, so that's a 2, we are fine right here. We are not crossing the plus minus 4 MAD bounds. 3, that's fine. 4 is fine. We are touching it, but we are not crossing is a 2.23, still below plus 4. 0.96, still below 4, and so on and so forth. But at this point right here, which is a 5.17, the forecast model, the forecasted value shows a behavior in which it suggests that this forecast model loses its statistical significance. And after that, you see 6 once more. So hence, if we consider the plus 4 and minus 4 as the bounds for the tracking signal value, then this forecast model somewhere around time period 8 and 9 loses its statistical significance. And this part right here suggests that there is a strong evidence of error bias in this particular forecast model, since it is crossing the standard of plus minus 4 MAD, which we adopted. Now, in other words, what if we plot the actual value with the forecast value, something like this? That should tell us something. And if you check this one, So that's the line, the actual line, and that's the forecasted line. And right here, this region, you see that there is a consistent positive error. And because of that, our forecast model is not in a statistical control. And that is how we establish that either a forecast model is in a statistical control or not. Let's take another data set. And suppose we have a data set, and let's suppose, and let me arrange a data set. That is the next example which we are solving right here. So that is another data set, a small one, just to once more do this estimation and establish that this particular forecast model having about 6 observation is in a forecast control or not. So the first step is to estimate error. So how to estimate error? That is actual value minus forecast value. So let's drag it down. And then the next step is finding the cumulative error value. So what's the cumulative error value for this? So it's this. And the next one is adding in diagonal right here. And let's extend it. And the next step is to estimate the absolute error value. So we'll do equal to AES, and we'll select the error value right here. And after that, we are supposed to estimate the cumulative absolute error. So what's the cumulative absolute error? It should be something like this, the first value right here. And then the next value should be 1 plus 3. And we'll drag it down. So we estimated the error value, the cumulative error value, the absolute error value, the cumulative absolute value, and after that we are supposed to estimate the MAD value. So how do we estimate the MAD value? We take the absolute cumulative value or cumulative absolute error divided by the observation right here, and let's drag it down. And finally, the value of a tracking signal. So how do we estimate that? We take the cumulative error and we divide it by MAD. And let's suppose in this particular case, we take the limit as a plus minus 3 MAD, right? So let's drag it down. Let's plot it. And if we plot this data, so here you go. This is one another control chart that shows the value of a tracking signal. And we took limits somewhat like this, plus minus 3 MAD. So right here, that's the lower bound. And since there are no positive MAD values, so by default, the Excel only took it till 150. So what's the conclusion? So once again, this forecast model is okay on the positive side of an error, but the tracking signal values, particularly for our time period 4, exceeds the lower bound value of a minus 3. And similarly, if we check this value out, so if I take it on side, so on 6th observation, again, the value gets out of the lower bound. So that was the bound value. So at 2 points, this model shows a error bias in that particular case.